Yeah, thanks. So after that very enlightening discussion, I hope, we're very happy to have Clifford Johnson, who is going to tell us about Fredholm determinants, I think. So if you're ready to share, Clifford, then please take it away.
Hello, everyone. Let's see. I tested it earlier. Hopefully it still works. And here we go. Is that visible?
Yeah.
Ah, excellent. Okay, and hopefully everyone can hear me.
If you can make it larger, it would be good.
No, I haven't started the
Okay.
thing yet. 1 second. And that should now be full screen. Is that correct?
Perfect. Yep, perfect.
Okay, shall I start?
Yes.
Yeah, please.
Okay.
You have a little pop-up on your screen with the
Oh no, have I?
built effects.
Yes, shouldn't see those. Showing all the, that's odd. Okay, I apologize. Okay, so I am going to get rid of all of that and hopefully it should go. So the discussion, has that gone now? Thank you.
Yes.
The discussion that we had just now, I think, is a nice indication of what I wanted to start with. Perhaps it's a bit old-fashioned to say this, and perhaps boringly controversial in some ways, but I think that we're not going to fully resolve all of these issues to do with black holes and other aspects of quantum gravity to everyone's satisfaction if we're sticking too much to approaches that link too much to space-time geometry. And what I mean is, again, the somewhat old-fashioned view that we know that geometry is likely emergent in a full theory of quantum gravity. And in some sense, we've perhaps been lucky in that we've had a remarkable number of successful computations that seem to be along the right tracks by picking various geometrical objects we like in the semi-classical approach and sprinkling some quantum stuff on it, and great things have happened. But I suspect, and maybe many of you agree with me, that that's only a piece of the story. And it might be that as long as we continue making different choices about what those favorite things are to play with, we're not going to all agree. So what I try and do is keep an eye out for tractable models of emergent space-time geometry, because I think we should learn from them. Let me say it a bit stronger. I think we should scrutinize models of that kind for lessons about how to perhaps use a different language to address some of this. And so, of course, one of the things that's been of interest to me has been JT gravity, because I think it's a great model of that sort of thing. Now, JT gravity on some manifold M is extremely interesting. It arises in a number of different contexts. For example, 2D quantum gravity in its own right, with black holes and wormholes and all kinds of interesting things. And of course, it also has a connection to the low temperature quantum dynamics of higher dimensional black holes. There's a whole ton of references I should give here, and I apologize that I haven't. Let me refer you to earlier talks that have talked about JT gravity and 2D quantum gravity. And for the high dimensional connections, I could refer you, for example, to a really nice talk by Sandeep Trivedi, I think last year or the year before in this strings series. But apologies to people I've not explicitly referenced. So the point is, what happens beyond that? And it's one of the things that I really hope that we can address in some model. And the reason it's interesting in JT gravity is because it's a toy model, but it has all of these interesting things, including the connection to higher dimensions. So that's the motivation for me. Beyond working on some manifold M, there is some story which is non-geometrical. And it's a model, once you include non-perturbative physics, where you can actually see the space-time geometry hand over to a non-geometrical description. And that's the sort of thing I think ultimately we need. So what has happened over the last 18 months or so is that I've developed various techniques for deriving explicit non-perturbative physics in JT gravity, and indeed not in just some formal sense, but actually allowing you to calculate things. And so in case I don't get to it, here are some things that you can calculate. The corrections to the Schwarzian that we all know and love. There are non-perturbative undulations that I will talk about. I'll show you how to derive those. You can use that to compute the spectral form factor that Steve Schenker talked about, for example. You can compute that fully in a non-perturbative sense in a full theory of JT gravity using these methods. And as came out last week, and I'll tell you a little bit about it at the end, a puzzle that has been in the literature for the last year or so involving how to compute the quench free energy. I can calculate that now, and there's the answer. So let me show you some of the things you need to be able to do that. So the key thing, first of all, let's remind ourselves about JT gravity. I'll be very brief. Here we have the usual setup. In particular, for the kinds of things that I'm talking about, I'll need to emphasize the fact that the Einstein-Hilbert action in 2 dimensions is, of course, topological. This parameter S0, which is the extremal entropy, is always going to is in front of that, and so whenever I compute on some manifold M with Euler number chi given by the number of handles and boundaries, I'm going to get a factor like that. And so we'll keep track. Topological expansion then will be this, and non-perturbative precisely will mean when I no longer have this expansion, beyond that expansion. So what do I have? I have a partition function, for example, the case of b equals 1, and it has some topological expansion plus corrections. And we do the usual things, and refer you to the papers, in order to compute the disk level, the leading order partition function. It looks like this. And by Laplace transform, I can extract some density of states, which is the famous Schwarzian. And there's a sketch of it. So what we're going to do in a number of steps is correct that Schwarzian, not out here in perturbation theory at large E, but deeply in here. So the landmark result on which everything stands that I'm going to do is the remarkable result of Shard, Schenker, and Sanford that the path integral, the JT gravity path integral on some manifold with factors like that then is connected to everything you compute here, you can compute here in a very nice framework, a double-scaled large N random Hermitian matrix model. There's an expansion parameter there, as Tuf taught us. The 1 over n expansion parameter is also a topological expansion, and it looks like that. So the matrix model looks something like this. There's some partition function. I've put a hat over it just to distinguish it from the previous partition function, which it is not. And there's some potential, which I'll call V. And if we're field theorists, we look at this as something we can do Feynman expansions of, and we write Feynman graphs. We draw their duals, and then we realize that the different vertices correspond to tessellating with different shapes. Interestingly, the double scaling limit means I take large N and I tune the couplings in that potential to some critical values such that large surfaces dominate. You end up in a limit where you have smooth universal physics of the gravity theory emerging, depending upon what the gravity theory is, which implicitly depends upon the potential that you chose. The triple S connection then is that there is some connection, not some connection, there's an equal sign between the partition function of JT gravity, for example, and an insertion of a thing that in the old language you might call the loop operator in the double scaling limit. Some important comments are that this is inherently perturbative, using some beautiful checks that they did based on topological recursion properties of the various objects that show up in doing the path integral as characterized by Mirzakhani, and then cast in loop equation language by Enyart and Orentin. It's important to realize that V is not explicitly known. It's enough because of those recursion relations to specify the leading spectral density, and then recursion tells you how the rest of it works out. And it is highly non-trivial and quite remarkable that it matches to all orders in the matrix model. I should also point out that there's a generalization and a classification to other models in the JT class by Stanford and Witten, which followed soon after. There are partial non-perturbative insights in these papers, but I think it's fair to say that the story was only touching on the beginning of the story. So I want to tell you one way of ending the story. So first, I think it's useful to go back to random matrix models and remind ourselves how they work. I'll use the simplest model I can think of, the Gaussian unitary ensemble. And this is simple enough that you can find all the equipment you need at home. So have a go. And you can simply take Hermitian matrices with some probability, some Gaussian probability. That's what that simplest model I wrote before with no higher order terms in the potential really means, as taught to us by Dyson. Not Dyson, by Wigner, or perhaps Wishart. We compute eigenvalues and then just histogram them, and this is what you get. So as you know, eventually what happens is that things settle down and there's a universal shape that seems to appear. I've done some scalings in order to write that shape, and it looks like this, and it's the famous Wigner semicircle law. Now, what the double scaling limit tells you to do is actually focus on an endpoint and zoom in. So I write lambda equals -2, say at this endpoint, plus a little bit. And there's a precise scaling you need to do in order to magnify that region with n. And if you work it out, the power of n is 2/3, and on the bottom line. And there's a parameter delta that I'll use as well to scale everything nicely. So you go ahead and you do that, you plug that into here, and you look at what happens to this, and you get this nice rearrangement. What I've done is I've gathered things together into this nice piece here, which I'm calling row 0 without a hat on it of E. And what I've done is I've defined a parameter h bar, which is sort of renormalized 1/n. As n goes to infinity, delta goes to 0 in the limit. And that's typically what happens in double scaling limits more generally with these models. Well, let's actually go back and just roll the dice again and have a look. And what actually happens if you zoom in that same way, you'll get this. Now, if I did a bit more, some more samples, I would fill that in, but you can see what's happening. There's a pattern developing, and that pattern developing is the actual famous wiggles that you get on top of the root E behavior. Now, that magnification captures everything I want to talk about in some ways. It's a toy model, but it's very good. It can be written in terms of arie functions, and there's an expansion in what I'm calling h bar, which is 1/n, but there's also non-perturbative pieces. Now, why is it called the arie model? That encourages me to tell you a little bit more about some of the useful technology, and that is orthogonal polynomials. What you can typically do is rewrite these matrix computations in terms of polynomials that are orthogonal with respect to the measure. Now I'm working in the eigenvalue basis. And there's some relation that looks like this. And it's sometimes convenient to rescale things by this factor here so that it's orthonormal, and then write the integral as some sort of bracket notation like that. There's a recursion relation between the orthogonal polynomials. And for example, in the Hermitian case that we were just talking about, these are actually Hermite polynomials. And the recursion relation, the recursion coefficient is just n, the index. Everything can be reduced to computing the Rn. And if I know these, I know the full answer. More generally, when I have V, you get a much more, you get much more complicated recursion coefficients. And so you end up with all the content still being in the recursion coefficients encoding V. Now at large N, I can write the index over big N as some continuous coordinate like that. The polynomials become functions. The recursion relations become functions. And in the double scaling limit, then these scaling pieces I talked about in the example before survive. So I get E surviving from lambda. I get some little x surviving some big X, which is valued in the reals. 1 over n becomes that renormalized quantity h bar. These p's then become these functions psi, and r becomes a u. If you actually dig a little bit deeper, you can ask what happens to the operator lambda when I stick it into the bracket formalism. And you can see what happens. It's basically this recursion relation here. When you do the scaled version of it, you see that lambda as an operator becomes a Hamiltonian with potential given by the recursion coefficients. This is now a quantum mechanical theory. The wave functions are the orthogonal polynomials, or the orthogonal polynomials become the wave functions, and the spectral density becomes, and I've done no approximation here, it turns out to be the integral of the square of the wave function over part of this X region. So that's the story. The Hermite polynomials themselves become arie functions and build the wave functions for us. And there's a beautiful story of how that all works, and you can do the integral and get what I wrote before. So that's what this looks like. Now, this is just a toy model. The arie model is not a model of surfaces. It is very interesting in its own right, but for here, it's just an illustration of the power of this approach, because I have all the tools I need now to tell you how this generalizes. The arie model, it shows us things through the fact that what I'm doing is I'm using this formalism. I have this little function u, this function little u, and knowing this potential in general is a great way of diagnosing problems and also figuring out how to define non-perturbative physics. And so my job over the last 18 months was to convert a lot of the known information, the known approaches into this language where you can get access to some of these crucial answers to some of these crucial questions. For example, arie has a precursor problem, a precursor of problems for triple S. There's a leaking non-perturbatively of energies into to negative values, and they are avatars of a full non-perturbative instability for the full triple S theory. You can see where that comes from in this language. It's simply the fact that when I do this integral, I pick up the tails of some of the arie functions that are at negative energy. That tells you also how to fix the problem. You simply don't have those tails. What you do is you look instead for potentials that are the same at high energy, so they'll have perturbatively the same physics, but at low energy, they cap off in this way. Now, I didn't just make this up. It turns out that there are matrix models that do that for you. And so you can actually write down a model of complex matrices with some potential that's built out of M dagger. So it's really, you can think of it as a model of Hermitian matrices that are intrinsically positive from the outset. It turns out that almost precisely 30 years ago, I worked on some of this stuff and helped develop the kinds of equations that you need as part of my thesis work. And so you can sort of go back and look at some of that work and see how to convert it into the modern language. And one of the things you see is that the resulting row, if you look in this paper, is very similar to the arie function, but then it ends very nicely at equals 0. So this isn't done by hand. There are matrix models that perturbatively are identical to the Hermitian matrix model that will give you better non-perturbative physics. Now, the challenge, of course, is to extend this to full JT gravity, and this is what I did and variants thereof, and this is what I did in a series of papers. What you have to do is you have to identify the Hamiltonian. So you have to find an equation for u, and the equation I briefly showed you on the previous slide is a form that you will always get for those kinds of models, but the content is different. I should have said a little bit more about it, but time is short. So there's some nonlinear equation you can write down for u, and you can solve it. It's tricky. It turns out that the equations are formally of infinite order, but you can truncate them. And if you truncate them to high enough order, I think 15th order will give you a good solution. You can solve that nonlinear differential equation with a bit of care. You'll get a u. You can then solve the spectral problem. Again, it's tricky, but you can do it. And then you can compute this. And here are some results. So there is a sort of potential you get for JT gravity. And this is the result. You get wiggles as promised. So this is by now fairly robust package of things to do. It gives you full non-perturbative definitions of JT gravity and various variants. These, I should remind you, are explicit results. not merely formal. So you can compute useful things with it. For example, the spectral density, as I did in those initial papers. You can really learn a lot of what happens non-perturbatively to some of the questions. The point is that you cannot get this plateau region and the crossover into it in any of the perturbative approaches to JT gravity. You need non-perturbative physics. So you can do more, refer you to the papers. And with collaborators, I also examined some other issues. There's some lovely work by Witten and also by Maxfield Chiriachi talking about deformations of JT gravity and how those look like as matrix models. And again, you can ask what's going on non-perturbatively with those models. And with Felipe Rousseau, I wrote a paper on that. With Rousseau and Svesco, there's a rather nice and mysterious model of Stanford Witten's, which is another JT gravity variant, which you can realize is a two-cut matrix model, and we did it in that paper. I should also mention that there's a lot of very exciting work that's adjacent to this, corresponding to minimal strings and Liouville, etc., that I think Thomas talked a little bit about, and that's relevant in terms of understanding how to build these models in terms of minimal string models, but I didn't have time to talk about that today. There are also other non-perturbative definitions discussed in SSS and also in Gao et al. Recently that are alternatives, and it would be very interesting to understand them, but right now they're very difficult to work with. You can't really calculate much with them. No disrespect intended, they themselves agree. So it'd be nice to have those developed and to put them alongside some of these and to calculate some of these things. Now, that's not all I wanted to tell you about. I don't know how much time I have left, but
Clifford, you have about 5 minutes left.
Really? Okay. Okay, so here we go. I'm going to go at breakneck speed and tell you, let's go back to the sampling that we were doing before. Okay. And now I'm going to say, instead, keep track of the order of the eigenvalues. You've got a matrix, keep track of the first, second, third, maybe color code them and run it again. And this is what you get. So what you see is now I've color coded things. I have different contributions, which are in some ways now telling you in some resolved way what those underlying wiggles are. Those undulations in rho, those non-perturbative undulations, this is the arie model, are in some ways the individual, well, not in some ways, they are precisely the underlying energy states, individual statistics. You have individual peaks. What happens very crucially is that they get sharper and more dense as you go to larger energy. And in some sense, they form a continuum. And that's the regime in which we do gravitational computations using manifolds, etc. As we go to this regime, that eventually breaks down. But what takes over are these states and their statistics. So the model doesn't care about what you call geometry. It just computes. And at the end of the day, we're up here doing things in terms of manifolds, etc. But down here, we have to use a different language. Now, this is just the arie model. You might ask, well, can I really do this for JT gravity? And the answer is yes. Let me tell you what the tool is that you need. So I'm just going to jump. There's another thing I wanted to show you, but I'm going to jump. And the tool you need is the Fredholm determinant in order to do this. We already have the components, it turns out, and that's the wave functions. So what you need is to put them together in a nice way. And it turns out you assemble them into what would be called, in the arie case, the arie kernel. You do this integral, and you can see it's actually a matrix for which the diagonal part is the spectral density that we talked about before. But there's a more general object, and all of that off-diagonal stuff has information in it, and we can use it. So in the random matrix model literature, you'll find kernels of all different kinds. One of the nice things is that JT and all its variants, as defined in the way that I'm using the language, defines a whole bunch of interesting new kernels. So that ought to be interesting. I was going to tell you why it's called a kernel and Fredholm, but there's no time. The key point is that the determinant of this thing is a very natural object in random matrix model literature, and I think it's a very natural object to use in gravity. And what you actually do is you can find out, for example, what's the probability of not finding, say, the first level in some interval, and you compute this object, unfortunately called E, and it's the determinant given as follows. That's a cumulative probability, so you need to take the derivative to get the probability distribution, and it looks like this. So far out here, I'm unlike I haven't found one yet. I start finding them, and by the time I get far out, I've probably found all of them. So that's the way to think about the cumulative distribution. Now the point is that you can get other levels by recursively using this in ways I don't have time to go into. It's a challenging problem to compute the determinants of these infinite dimensional operators, but it turns out that there are some techniques due to Bornemann that are very helpful, and I can do it for JT gravity, and this is the answer. So this is our third refinement, our second refinement of the Schwarzian. There's the Schwarzian, the dotted line. There's the wiggled lines that I found last year in a variety of models, modifying, finding non-perturbative contributions. And now you can resolve what deserves to be called the individual microstates. And the really very important thing here is that this is not just a two-dimensional model. This also tells us about higher dimensional black holes. And so in some sense, in some limit, we're also getting access to a description of the higher dimensional black hole microstates. Let me remind you then, the geometrical description is good in this direction. These essentially become spikes and form a continuum, and gravity and geometry takes over. And in this direction, you need something else. And the matrix model can do all of it, and it's completely tractable. So that's why this is interesting. If I have all of the microstates and all of their statistics, I can actually compute everything. That is the complete matrix model. And I do have all of that. So I can compute, for example, something that's hard to do from other perspectives. I can compute the quench-free energy. The quench-free energy is very important because I need to follow the thermodynamics all the way down to low temperature. There's some really
just let
nice...
you know you're running into your question period.
Okay, I'm going to take one more minute. Thank you. There's some really nice discussions, for example, by Englert et al. About using replica wormholes to compute it. One of the things that I emphasized in an earlier paper is that you really need to get access to the non-perturbative physics to finish the story, perhaps the matrix model. There have been various papers that have found some partial results, but now we can just do it with all of these microstates that we have, and that's the answer. So in view of the time, I think I'm going to stop here, make some comments. There was another movie to show you how that all works, but there isn't time. There's some comments about how this realizes some of the things that were anticipated by some authors at the very low energy level, but this is the full thing. No toy model, no approximations. This is the answer. I should also mention that sadly, there's no sign, as I guessed last year, of replica symmetry breaking. It seems that the matrix model isn't interesting enough. So I'm going to jump to the end, and thank you.
That's all. Thank Clifford. And if there are any questions, then please raise hands. Julian.
Yeah, hi, thanks. First of all, Clifford, thanks. It was a really clear talk. I enjoyed it a great deal. So these new matrix models, I just wanted to know, maybe you can say a little bit more about their properties. So in particular, since they are not Hermitian matrix models, I mean, how do they arise, for example, as a boundary theory or as a limit of some boundary theory?
That's a great question. First of all, I should say, in some sense, they are Hermitian matrix models. They are, you know, if you just were doing perturbation theory, which is what we've been doing, and you started out and you were saying, oh, I must use some Hermitian matrix model, you could well have just started with these. Traditionally, we start with the less constrained type, but the fact that these are Hermitian matrix models with which are positive is it really comes in only when you get to the non-perturbative sector. So, you know, if you ran history differently, perhaps you would have started with these. Ironically, actually, history did run differently. Wishart matrices, in fact, are what these are in some ways. The Wishart matrix models, which predate what Wigner did in the 50s by some 20 years or so.
Okay, thank you.
Yeah. So I think we're to give Kristen his proper time. We're probably should move any other questions to the discussion session, which I think immediately follows Kristen's talk. So Igor and Sandeep, write your questions down for Clifford. But let's thank Clifford again for his.
They should go first then,
wonderful talk.
and I'll be around for the discussion. Thanks, everyone.
So Kristen, if you're there and ready to go, then